I create this quotient group, factor group G mod H, starting from some normal subgroup. And we looked at 5z in the integers. We said, hey, wait a minute, this is what gives me z5. That's true in general, because I know that nz for n, any integer, is a normal subgroup in Z. I know that because right, but I haven't looked at those. How do I know that's always true? That's what it means to be normal. How do I know that applies in this situation?
Because when you divide z by n, nz, you get n, and that's how you calculate your nz.
That just tells me how I get the coset. Again, it doesn't tell me that the left coset containing 3 is the same as the right coset containing 3. Why do I know that is a true statement?
Multiplications, Susie.
What group operation do I do in Z? It isn't the fact that it's associative, because that's true in every group. It's abelian. It's commutative. So every subgroup in the integers is automatically a normal subgroup because the integers under addition are abelian. And so when I do Z mod nz, I get exactly n cosets, and this turns out to be isomorphic to Zn. No matter what n I pick. Brilliant. As a matter of fact, this is cyclic, which means one of the cosets is going to be a generator. What's the generator for the integers? What's a generator for the integers? So the coset that contains 1 is a generator for the quotient group.
Question, but for the like once like G mod H, you rewrite it like on that fraction, does it have to be like a slash?
You can be horizontal if you want. You write it however you like. As a matter of fact, some textbooks, the notation we use for index G colon H has also been used for this factor group as well. I don't like that one as much because I want to use that for index, but different textbooks have different formatting setups. My personal preference to that slash, it's just annoying to try and write it horizontally when the fraction is smaller. A lot of times I end up writing it just all on the same line with that diagonal fraction.
Okay.
Let's move from the integers to the real numbers. The real numbers don't have a generator. They're not a cyclic group, but they are still a group. Let's go with just the general real numbers. But I could make a cyclic subgroup, pick a positive number, and look at the subgroup generated by that. Again, I'm going to use addition because I'm using the entire real line that includes 0. Can't use multiplication if I include 0. I've got to use addition. Under addition, the subgroup generated by C is all the multiples of C. 0, C, 2C, 3C, 4C to get closure, minus C, minus 2C, minus 3C, etc. to get inverses. But since I'm using addition, this is normal in the real numbers. So what does this look like?
There be infinite cosets.
Yes, absolutely. There will be infinitely many cosets. But how do they differ? What tells one coset apart from another? Let's do a concrete example. Somebody give me a real number. Make it easy on us. Pick a number. 4. There's the subgroup generated by 4 under addition in the real numbers. What's a coset of this?
Plus 4.
But since I'm using real numbers, I could have any number out there, not just an integer, right?
So n.
Well, right?
Yeah.
Anything I want. A half. So let me think about that. If I did A plus the normal subgroup generated by 4, how many different A's? There are infinitely many. If I asked you to pick the smallest non-negative A you could for each of these cosets, I've already done that. But what will you then be able to say about all of the A values that we pick? If my goal is to pick the smallest non-negative A in each of these cosets, that A must be between 0 and 0 and 4. And it's never going to be equal to 4, right? Because as soon as we get equal to 4, then we're back where we started with 0, right? Okay, wait a second. Think about the open, half open interval we've just listed from 0 to 4. When we think of Zn, we think of a clock, right? It wraps back around. I want you to think of this interval. When I tell you to picture an interval, I apologize. What do you see if I tell you to picture an interval? Most of you, I expect, would see a number line with 0 marked on one end and 4 marked on the other end, and like a closed dot and an open circle because it's a half open interval, right? I don't want to do that. Just like Zn is a clock that wraps around, I want to think of this interval as wrapping around. So instead of writing the interval 0 to 4 like this, I'm going to write it like this. Instead of marking off 1, 2, and 3 on the straight line, I've turned my straight line into a circle by bending it around so that the dot and the open circle overlap each other. Just like 0 and n overlap each other in Zn. I'm so happy that they're unloading right outside. What we've created is the real line mod 4 rather than the integers mod 4. And so instead of having 0, 1, 2, 3, I get everything from 0 to 1 to 2 to 3, all the way up to, but not including 4. And then I wrap back around. And we've created the group R4 under addition mod 4. Now, before you freak out on me and say, this sounds stupid, you use this in really simple places. Let's go, instead of using 4, what if I used 2 pi? Then you'd add angles, wouldn't you, right? 3 pi over 4 plus pi over 6, I can do that, right? I can add those angles. 7 pi over 4 plus 3 pi over 2 is bigger than 2 pi. Who cares? We just take off the 2 pi, don't we? We get the reference angle, the angle between 0 and 2 pi. That's what we're doing. We're doing the real line mod 2 pi, which means this group is isomorphic to a circle.
What's another group we know that uses a circle?
Well, U4 just was distinct, right? It'd be the whole unit circle, wouldn't it? So this is actually isomorphic to the complex unit circle under multiplication in complex numbers. Son, you're looking at me like you still hate that. No? Okay. I misread your expression. Okay, I'm allowed. Either that or it's the fact that it's a Thursday morning and you're all like that. The whole separate ball. Question. I started with a normal subgroup. And I know that for every homomorphism, there is always a normal subgroup, right? If I have any homomorphism, then I know that the kernel of that homomorphism is a normal subgroup in G. And remember, the kernel is the set of stuff that gets mapped to the identity in the other group. is there a homomorphism from the integers to something whose kernel is NZ? Is there a homomorphism from R to something so that the kernel of that homomorphism is the subgroup generated by 4? In other words, instead of starting with a normal subgroup, can I use a homomorphism every time? It turns out that if you have a normal subgroup, you can always create a homomorphism. The homomorphism gamma from the group to the set of cosets, G mod H, the factor group. Given by gamma of X is the left coset containing X. That's a homomorphism. What's more, the kernel of that homomorphism is exactly the normal subgroup we started with. So what this actually gives me is a connection. Normal subgroups go with homomorphisms. Homomorphisms create normal subgroups, both directions. By the way, the proof of that theorem is a whopping 2 lines. In order for me to have a homomorphism, I have to satisfy the homomorphism property. Gamma of X, gamma of Y. But gamma of X is XH, and gamma of Y is YH, and those are cosets. And when we're in cosets, when we multiply cosets, we multiply the corresponding elements. Yes? But isn't that the same as gamma of XY? There's the homomorphism property. And XH is equal to H if and only if X is already in H. And that would mean over here, in my collection of cosets, that gamma of X is equal to the identity coset, E. Well, wait a minute. The coset that plays E is EH. So H is the kernel. I can hear in the backs of your heads, because I can see it written clearly on some of your faces, so what? What does this get me? Well, it turns out what this gets me is the canvas picture for this course. Fundamental homomorphism theorem. Now, the statement of this theorem is not all that straightforward. So let's walk through this carefully. We're going to start with some homomorphism, phi from group G to group G prime. Because it is a group homomorphism, it has a kernel. Let's take that kernel and we will call it H. What does that symbol mean? Phi square bracket G. That's back in our section on homomorphisms. What does phi square bracket G mean? Aha. So I'm looking at the whole image. Now remember, G prime is the codomain. We have domain and codomain. Phi of G is the range. It's the actual image of what happens. That could be all of G. It could be it could be all of G prime. It might just be some of G prime. But by our properties of homomorphisms, I know phi of G is a group. And that makes it a subgroup of G prime. And now I can think of the homomorphism we were just talking about. The homomorphism gamma that goes from G to the cosets. Because I have cosets of H. But I also have this map going to G prime. So for the moment, I'm just going to put this over here on this board. I have the group G. I have the map to G prime, phi. I have the normal subgroup H, and I have the cosets And this is the map gamma that we were just talking about. So far, so good? Close the triangle. There's got to be a map there. Let's call that map something. Let's define the map mu from the cosets to phi of g given by mu of a coset is phi of x. So I take each coset onto its image. So that would be that dotted arrow over there in the picture. That would be our map mu. I'll go back over there and I'll label it. That map is an isomorphism. And that diagram, that triangle that we've drawn, shows me that phi is decomposable into looking at the cosets and then looking at this isomorphism. Copy the picture over here so it's in the notes for us to see it. What we've really done is we've factored our homomorphism, phi, using this factor group of cosets, and then saying, hey, the structure we get here is isomorphic to the structure we have here. Which is why I was able to say that Zn is isomorphic to the coset behavior Z mod Nz. Okay, I need you to cast your mind back to discrete math, because that's where we did this the first time. I didn't phrase any of it in this language, but we did exactly this. When we talked about that set, then we said, hey, wait a minute, there are conjugacy classes. There are the things that are related to each other mod 4, right? And we came up with 3 other sets. And then what we said back in discrete is, hey, if you put any two numbers you want over here on the right, and then take the remainder when you divide by 4, that's the same as if you add any of these numbers over here on the left, 0, 1, 2, or 3, and take the remainder when you divide by 4. So the behavior of the regular ordinary integers correlates with the behavior of these cosets. That's this map gamma right here. And then I said, no, this. We're going to think about dividing by 4 and looking at remainders. And then we take the entire set of integers and we map it to this set. This is the map phi. Phi says divide by 4 and take the remainder. And we had no clue what that meant. So we wrote out the word mod. And y'all were like, how does this work? And so we did a bunch of examples. We did 4, we did like 17, we did 63 at one point, 57. We did a bunch of these, right? All sorts of calculations in mod. But what I'm saying is, no. I don't have to think about just working with these numbers. I think about working with these as sets. And that's working down here. So what I've written right here is the map gamma. The map gamma takes the integers to the collection of cosets. Where is the map mu in this argument?
You're like going from the bottom, like 4z, comma 1 plus 4z, and going just straight up to 0, 1, 2, 3.
That's a 1-to-1 and onto map, isn't it? 4z goes to 0, 1 plus 4z goes to 1, 2 plus 4. And there's my 1-to-1. That's an isomorphism, damn it. Mu of a plus 4z is equal to a. Where a is between 0 and 3, inclusive. So this is actually where modular arithmetic comes from. We didn't make it up as a rule in discrete. Randomly, we actually got that idea from this group discussion. This built modular arithmetic. I picked 4 out of thin air because we did 4 in discrete. Otherwise, I wouldn't have used it. I would have used whatever number we'd used there. But I remember this example now. Drilled it into my head for 20 years teaching discrete in different times. So I keep using the same number. But think about what we did with the real line and the subgroup generated by 4. Instead of just having 4 cosets, we'd have infinite many cosets, right? And every coset would be identified with some number starting at 0 up to but not including 4. And if I added 2 numbers over there that were real, their remainder after dividing by 4 is somewhere between 0 and 4. And that's where I get that picture of a circle from. That means that modular arithmetic can be extended from just looking at integers to looking at any set of numbers in the real life. The critical statement out of all of this is that factor groups and homomorphisms are changeable. Every homomorphism gives rise to some factor group, and every factor group has built into it some homomorphism. Now, it may be an absolutely weird method of describing a homomorphism to give the factor group first, but there are cases where we want to look at a factor group and try and analyze what its structure is. I promise there's a reason for that. I want you to think about the group Z4 times Z2, the Cartesian product. First question, how many elements are in Z4 by Z2? Z4 times Z2. 8. And you could write them all down, right? 0, 0, 1, 0, 2, 0, 3, 0, 0, 1, 1, 1, 2, 1, and 3, 1. There we go. That's all of them. How many elements are in 0 by Z2? It should just be 0, 0, and 0, 1. Great. Wait a minute. I've got a group of 8 things, and I've got a subgroup with 2 things. How many cosets do I get? This is why I use dividing. What do those 4 cosets act like? What does the collection of cosets that I get act like? It's a group of order 4. There are 2 of those. Which one is it?
I don't know.
Is the result of our factor group going to turn out to be Z4, or is it going to be the Klein 4 group, V? I don't know off the top of my head. But think about that picture, our fundamental isomorphism theorem picture, fundamental homomorphism theorem picture. I can say, well, if I can figure out some homomorphism where 0 times Z2 is the kernel of that homomorphism, I can figure out what phi of G is. Remember, phi of G is some subgroup of G prime. So if I can figure out what phi of G would look like for the right homomorphism phi, then I can figure out what this group looks like. So let's think about some homomorphism is going to start in Z4, Z2, and is going to have kernel 0 by Z2. I will freely admit, this is not obvious that there is such a homomorphism is required by that theorem. But figuring out what it is not really easy off the top of my head. I do this visually. I will do more of these visually next week, but I do this visually. I think of Z4 by Z2 just like the Cartesian plane. We call it a Cartesian product, don't we? So let's make a Cartesian plane picture. Z4 will be on the x-axis, Z2 will be on the y-axis. I'm going to get 8 dots. Rather than a whole axis of numbers, I'm just going to get 0, 1, 2, 3 in the Z4 direction. And then I'm going to get 0 and 1 in the Z2 direction. But I get 1, 1, and 2, 1, and 3, 1. Those are my 8 dots because we said there were 8 things that lived in this group. Right, Reese? Do me a favor. Circle the dots that make up our normal subgroup, 0 by Z2.
Like circle more than one dot at once?
Yep. Or circle them individually and then connect them somehow. But I want you to indicate those 2 elements differently than the others. That's these 2, right? I want both of those to get mapped to the identity. In Zn, the identity should be 0. So I want a map that takes those and results in something that is an identity. What's a map? Takes both of those and compresses. There's a linear transformation that does that, people. Chapter 1, sections 9 and 10 of the linear textbook. I'm evil for having taught both classes and remembering this from last year. A projection. Project onto the x-axis ignores the y-axis, doesn't it? So I would squish this down. But then I could also squish these down, couldn't I? And this down. Holy crap, I found a homomorphism. The homomorphism in question goes like that. It ignores the second component and it maps it to 0, and the first component stays the same. Yes? So this homomorphism, P1, pi 1, goes from Z4 by Z2 to Z4 by Z2. In the picture over there, in my homomorphism theorem triangle, G prime is the same as G. What's the range? What's the image of this homomorphism?
What's the precise definition of an image again?
It's the collection of things in the codomain that are hit by something in the domain.
Gotcha.
So I want you to do this pi 1 map to every one of these dots and tell me what dots you get as answers.
It'd be like Z4 and then 0.
Yes. And you just said that, Reese, the magic way. Because if I still think about using these under addition, wouldn't I be adding Z4? And the second coordinate would always be 0? Which means this is isomorphic to Z4 times 0, which is isomorphic to Z4 itself. We figured out which group of order 4 my cosets behave like. They behave like Z4, not like the Klein 4. Ready for the picture part of this? There should be 4 cosets in that picture. They should be correlated with our normal subgroup, shouldn't they? The coset that goes with 1, 0 is this vertical The coset that goes with 2, 0 is this vertical oval. The coset that goes with 3, 0 is this vertical oval. They're right there, and they're parallel. They're correlated with. Stop. There's a visual here, I promise it works. The question is how to picture this in the general, more abstract case, and that's going to blow our mind. We're not doing that today. This sort of factor group calculation, in particular when looking at infinite groups, like R and the integers, and the general linear group of matrices, and all of those sorts of things, give rise to really, really, really powerful results. Not just in math, in engineering, in physics, and in so many other, in geometry. There are results here in geometry that will absolutely be astounding. I skipped it, but chapter 11 is all about wallpaper. That sounds stupid, doesn't it? Have any of you ever put up wallpaper? I want to tell you it is the most thankless job in the entire universe, trying to put up wallpaper. It's worse than painting a fence. Tom Sawyer had nothing on, Huck Finn had nothing on putting up wallpaper. Because not only do you have to get all the sheets to hang correctly and smoothly on the wall, you have to line up the patterns perfectly between the edges, which means you're matching symmetry of the pattern. How many symmetries are possible in wallpapers? Well, it turns out those are parts of our symmetry groups, like the dihedral groups. And it includes one other possibility, a glide mirror, a glide transformation. Turns out there are exactly 17 wallpaper groups. Chapter 11 talks all about them. But that's a freaking geometry result out of here. Whew. I will do more of these next week. Lots more of them. And look at some of these larger results. Questions? I hated putting up wallpaper. I do it in 3 different houses. I don't ever want to do it again. So it turns out that if I want to find these homomorphisms, I really want to find normal subgroups. And if I have a subgroup, I can ask the question, is this particular subgroup normal? And as we saw from looking at D4 and D3, and some of the questions in this homework that you just turned in, some of these are hard. Especially if the group I am looking at is not something whose operation I am familiar with. Like the dihedral groups or the permutation groups. Those are not intuitive, clear, and obvious automatically, and those suck. So what are some other ways I can do this? Well, wait a minute. What's the definition of H being normal in G?
The left cosets equal to the right cosets.
So the left cosets equal the right cosets. That's my definition. I want things that match this. So let's think about this for a second. If I have the left coset equals the right coset, that means if I pick something that's in the left coset, That should also be something in this coset, right? But everything that's written in the right coset is written as something in H with G on the right, isn't it? So that means that GH1 should be equal to H2G for every H1, H2 in G, in H. Well, for every H1, my choice of H2 will be fixed. There's got to be one that makes it work. If GH is equal to HG. Well, another way to say that is that GH1 G inverse is equal to H2 for some H2 in G. I like that. I like that expression. I've seen that expression before. Some of you have and some of you haven't. Depends on where you are in linear. I don't think you've seen this from matrices yet. This is going to come up again. What does that abbreviation stand for, TFAE? I've used it in a whole bunch of classes. The following are equivalent. So that idea that when I do GH, G inverse, I get something in H is equivalent to taking the whole group H, multiplying by G on the left and G inverse on the right, and getting some other version of H back, rearranging stuff. Being a normal subgroup is equivalent. It's defined by property 4 here, right? Left coset is the same as the right coset. But our homomorphism theorem tells me, number 3, that H has to be the kernel of some homomorphism. And the calculation we just did up there says that putting a G on one side and a G inverse on the other side should keep me in H. This one here, these two, they actually help me define a new idea. Now, the calculation we did actually proves 1 and 2. 3 was part of the fundamental homomorphism theorem, and 4 is the definition. I'm going to create a function. Take any group you want, pick an element, G, in that group, and we're going to do this G times X times G inverse for any X. That's an isomorphism. Sure it is. How do I prove this map is an isomorphism? What do I have to do?
Need a bijection.
From G to G, right? Which means it needs to be 1-to-1 and onto. But there's more.
It also needs to be a homomorphism, right?
I need the homomorphism property and a bijection. Yes. Proof. 1. Is IG a homomorphism? Well, that means I need IG of X times IG of Y, and I should end up with IG of XY. That would be what the homomorphism property tells me, right? Multiplying after the function is the same as multiplying before the function. What is IG of X? Well, I wrote that down. That's GX G inverse. What's IG of Y? I love it. We are in a group. What happens?
The
I'm not disagreeing with you. I hope to get XY, but how do I get there from here?
you can move parentheses around.
My group is associative. And if I move my parentheses around, I can rearrange it to write GX, G inverse G, Y, G inverse. What happens in the middle? Poof. And then I get G, X, Y, G inverse. Where can I put the parentheses now? And that is exactly the definition of IG, XY. It's a homomorphism. Reese, how do I show it's 1-to-1?
Because unique to each element. Each element has a unique output.
Yes. How do I do that? That's exactly what I want to do. How do I do that? The definition of 1-to-1 as written in the discrete book, chapter 2, section 4, where we did functions.
But every element is every element in G is going to have a map to it.
That's onto. That everything gets hit. We are on everything. How do I show it's 1-to-1? You said show that each thing is different, right?
Mm-hmm.
So let's assume they're not different. And that means if they hit the same thing, they had to come from the same thing. suppose IG of X is equal to IG of Y. I want to end up with, oh, well then X must be the same as Y. But what is IG of X? Oh, we wrote that down up here. G, X, G inverse. And over here, G of Y, IG of Y is GY, G inverse. We are in a group. What happens?
You multiply on the left by G inverse and then on the right by G.
With a little bit of rearranging of parentheses, what's the next line?
X equals 1.
Yay! To show it's on 2 weeks, I have to show that everything in G gets hit by something. So, suppose Y is in G. What is the something that I can put here to do IG a thing and know that I'm going to get Y out? I want to solve for that question mark, which is the reason I didn't give it a name.
I don't know what it is yet.
But I know that doing IG to something is G times the something times G inverse. How do I figure out what something is?
That have to be like an identity,
Would which part of it have to be an
a
identity?
question mark.
Then this side, if this is E, then that's G times G inverse, and that has to be E. But I don't know that that's E. We just picked an arbitrary thing in G. I'm going to do a suggestion for 1-to-1 again. I'm going to multiply by G inverse on the left and G on the right. Question mark must be G inverse Y G. And since G is a group, this is an element of G. Y is in G, G is in G, G inverse is in G. Hey, if you want to hit Y, start here. Everything gets hit. Hot damn. Now, here's an interesting part. I have an isomorphism from the group to itself. We use these a lot. We use these so often we get them a special name. An isomorphism from G to G is called an automorphism of G. The automorphism we were just talking about, IG of X, is an inner automorphism. Of G by little g. And it's usually called conjugation. By G. So this particular automorphism conjugates a group. Hey, wait a minute. Our normal statement, following our equivalent, used conjugation, didn't it? And it said that H is only conjugate to itself. That means H is invariant under conjugation, if and only if it is normal. Now, what happens if my subgroup is not invariant? Well, then it gets mapped to some other subgroup, right? If it didn't stay the same, it'd have to go to some other subgroup. And so I have collections of subgroups that are conjugate to one another. When we did our subgroup diagrams, we had all these little different subgroups in there, right? If we had several different subgroups of the same size, some of them would be normal, some of them might not be. Which ones behave the same way depends on which ones are conjugate to each other. If H and K are both subgroups of G, K is a conjugate subgroup of H if there exists G in G with IG of H equal to K. A normal subgroup is conjugate only to itself. But that means the rest of the subgroups can be permuted. And that means that conjugation is a permutation within a group. Look, everything comes back to permutation groups eventually. They're under all of it. Automorphisms and the set of automorphisms themselves form groups. I hear in the back of my head, it's turtles all the way down, man. Groups are everywhere. They infinite descent. I will talk more about the precise calculations we do next week. I'd also like to point out to you that it took me 2 days to cover this section, which means you don't have a homework due on Tuesday for a change. I'll see you all then.